And now in this lecture I'll answer two questions. The first question, we find out the radius of this circle, and the second question, we will find out the area of this circle using two different methods. So we start with the first question. In the drawing we have a circle. We know that we have also the right triangle ABC. This is angle ABC, this is right angle. Side AB equals to 13 units in its length. According to what is given us in the question. Line segment AD also equals to 13 units in its length. And if side AB equals to 3 units in its length, side AB equals to 3 units in its length, and side AD also equals to 3 units in its length. This is line segment DC is equals to 1 unit in its length. Point O is the center of this circle. Again, our task is to find out the radius of this circle. So here we can implement rule 25. Okay, click on rule 25. According to rule 25, if from a common external point you will draw a tangent to a circle and a line segment that cuts the circle at 2 points, then the following equation is true, that PA square equals to PB times PC. So in the moment we have a circle. This is the common external point P. From this common external point P, we have tangent PA that is tangent to this circle at this point A, and we also have line segment PC that cuts the circle at 2 points, points B and point C. So in this way, the following equation is true, that PA square equals to PB times PC. Again, PA square equals to PB times PC. So we can actually implement 25 in our drawing. Why? Because in our drawing, if we focus on this common external point C, from this common external point C, we have tangent CE, that is tangent to this circle is point E, and we also have line segment CA that cuts the circle at 2 points, points D and point A. Again, we have line segment CA that cuts the circle at 2 points, point D and point A. So all the requirements for full 25 are satisfied, and therefore we can implement here rule 25. According to rule 25, we get that CE square equals to CD times CA. Again, CE square equals to CD times CA. So, write it down. In the common external point C, according to rule 25, CE square, that is the square of tangent CE, equals to CD, this is the small line segment CD, times CA. Again, according to rule 25, if we focus on the common external point C, the following equation is true, that CE square equals to CD times CA. CE is the missing tangent, so we leave it as it is. It is CE square equals to CD. CD equals to 1 unit in its length times CA. CA in total equals to 3 plus 1, that is 4. CA equals to 4 units in its length. So in total we found out that CE squared equals to 1 times 4. 1 times 4 is 4, so CE squared equals to 4. Here we take a root out of this equation, and we get that CE equals to the square root of 4, that is 2. CE equals to 2 units in its length. Tangent CE is equal to 2 units. So write it down. In the next step, we will implement the Pythagoras theorem on the right triangle, triangle ABC. So I copy triangle ABC, and then we will implement on it the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Side AB of the right triangle ABC equals to 4 units in its length. Side BC is the missing side, and the hypotenuse AC equals in total to 3 plus 1, that is 4. Here by PT is the evaluation from Pythagoras theorem. So this is the right triangle ABC that the common from the original domain. This right triangle ABC according to the Pythagoras theorem. AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. So write it down. AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is 4, therefore AC squared is 4 squared, that is 16. And it is equals to AB squared. AB is 3, therefore AB squared is 3 squared, that is 9. Plus BC squared. BC is the missing side, so we leave it as it is. So in total, we actually found out that 16 equals to 9 plus BC squared. Here we subtract 9 from this equation, and we get that 16 minus 9 is 7, so 7 equals to BC squared. BC squared equals to 7. Here we take a root out of this equation, and finally get that BC equals to the square root of 7 units in its length. So this is side BC. It is equals to the square root of 7 units in its length. So what is the length of the missing line segment BE? From the drawing, it's very easy to see that BE equals to BC minus EC. Again, BC minus EC equals to BE. So the norm BE equals to BC minus EC. So BE equals to BC equals to the square root of 7 units in its length. minus EC. EC equals to 2 units in its length. So in total we found out that BE equals to square root of 7 minus 2 units in its length. B equals to the square root of 7 minus 2 units in its length. Tangent BC is tangent to this circle at point E. Again, tangent BC is tangent to this circle at point E. So we join points O and E together by a straight line. Point O is the center of the circle. Point E is the point of the circle itself, therefore OE is the radius of this circle. We find the radius of this circle as R, therefore OE equals to R. The radius OE is equals to R, the radius OE is 1 to point E, that is the point of tendency of tangent BC with this circle. And whenever your radius is 1 to the point of tendency, then tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we'll do a construction. That is to say, from point O, that is the center of this circle, we'll go perpendicular on AB. Again, from point O, we'll go perpendicular on AB. So here, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AB. This point is point F. By doing this construction, we're going to do quadrilateral OFBE. Inside quadrilateral OFBE, we have 1, 2, 3 right angles. The sum of 3 right angles is 230 degrees, so 230 degrees plus the size of this 4 missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4 missing angle must be equal to 90 degrees in its size. So inside quadrilateral FOEB, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral FOEB as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle FOEB, side OE equals to the opposite side FB. But OE is the radius of this circle that equals to R, therefore FB must be also equal to R. Likewise, according to the same rule, in the same rectangle FOEB, side BE must be equal to the opposite side FO. But B equals to the square root of 7 minus 2. Therefore, the opposite side FO must be also equal to the square root of 7 minus 2 units in its length. What is the length of the missing 9797 AF? From the drawing it is very easy to see that AF in total equals to AB minus FB. Again, AB minus FB equals to AF. So it is known AF equals to AB minus FB. So AF equals to AB. AB equals to 3 units in its length according to what is given as the question, minus FB. We just right now found out that FB equals to R. So in total, we found out that AF, the missing side AF equals to 3 minus R units in its length. AF equals to 3 minus R. In the next step, We join points A and O together by straight line. Point O is the center of the circle, point A is the point of the circle itself, therefore AO is the radius of this circle, that equals to R. In the next step, I'll copy the green right triangle AF4 in a new page, and we will implement the Pythagoras theorem on this right green triangle, triangle AF4. So actually, this is the right triangle AF4 in the form from the original drawing. In this right triangle AF4, AO squared, this is the square they are produced, equals to AF squared plus FO squared. So let it known. AO squared, this is the square they are produced, equals to AF squared plus FO squared. AO equals to R, therefore AO squared equals to R squared, and it is equals to AF squared. AF equals to 3 minus R, therefore AF squared equals to 3 minus R squared plus FO squared. FO equals to square root of 7 minus 2, therefore FO squared equals to the square root of 7 minus 2 squared. So now if you found out that R squared equals to 3 minus R squared plus square root of 7 minus 2 squared. So R squared equals to 3 minus R squared. 3 minus R squared equals to 3 squared, that is 9, plus R squared, plus 2 times 3 times R, that is minus 6R, plus 7 minus 2, plus square root of 7 minus 2 squared. Square root of 7 minus 2 squared equals to 0.417. So in total, if you found out that R squared equals to 9 plus R squared minus 6R plus 0.417. Here we have R squared on both sides of this equation, so R squared will get cancelled. Once you cancel R squared, in this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 9 plus 0.417 equals to 9.417 minus 6R. So if you found out that 0 equals to 9.417 minus 6R. Here we get 6R for this equation, and you get that 6R equals to 9.417. Here we will divide this equation by 6. If we get it R equals to 9.417 over 6. 9.417 over 6 is equal to 0.57 units in its length. So if you found out that the radius of this circle R equals to 1.57 units in its length. So finish with the first question. In the next step, I will present to you the second question, and we'll solve the second question by using two different methods. In the second question, our test is to find out the area of this circle. So in the drawing, we have a circle. This is line 7BC. This equals to 6 units in its length. This is line 7BA, or this equals to 13 units in its length. Or this is chord BA. Chord BA equals to 13 units in its length. This is line 7CD. This equals to 18 units in its length. This is angle ABC. This is a right angle. This is angle BCD. This is also a right angle. Again, our task is to find out the area of this circle. So here we can implement rule 27. Those two one-sided interangles. The sum of those two one-sided interangles is 90 degrees plus 90 degrees is 180 degrees. And whenever you have the sum of two one-sided interangles that is equals to 180 degrees, then they must look located between parallel lines. This is to say, line segment BA is parallel to line segment CD. So in page 27, according to rule 27, if the sum of two one-sided interangles is equal to 180 degrees, then they are located between parallel lines. In the drawing, we have line A, line B, and the red line C cuts the two lines A and B. Those are angles alpha and beta that are defined as one-sided interangles. The sum of those two angles, alpha and beta, is equal to alpha plus beta is equal to 180 degrees, and therefore, according to this rule, rule 27, line A is parallel to line B. So we can implement rule 27 in our drawing. Why? Because in our drawing, the sum of those two one-sided interangles is equal to 180 degrees, and therefore those two angles are located between two parallel lines. That is to say, BA is parallel to CD. So as is known, chord BA is parallel to chord CD according to rule 27. So in the next step, we'll define the center of the circle. This point is point O, and we'll draw perpendicular on line segment CD and we'll extend the perpendicular until it touches side BA, or chord BA. Repeat again, from the center of this angle, that is to say, this is point O, we'll go perpendicular on CD, and we'll extend the perpendicular until it touches chord BA. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O and line 7 CD. This point is point M. We extended the perpendicular OM to chord BA. Because of the fact that CD is parallel to BA according to rule 27, it means that the perpendicular to CD will be also perpendicular to BA. Because of the fact that those two lines are parallel to each other, the perpendicular to this line CD must be also perpendicular to chord BA. Therefore, this angle also equals to 90 degrees, and this angle equals to 90 degrees from the rule that I mentioned. We define the touching point of the perpendicular from point O and chord BA. This point is point N. So ON is a perpendicular, and as a perpendicular it is absolutely a straight line. So if you focus on the upper side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line ON at point M? We have this angle that is a right angle according to our construction, plus this missing angle. In total, the sum of those two angles, they must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees in its size. You can actually conclude that this angle equals to 90 degrees in its size according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. In quadrilateral CB and M, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total, they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral CB and M, we have 4 right angles. And therefore, according to rule 5, quadrilateral CB and M is a rectangle. So it is known quadrilateral CB and M is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in a rectangle BCMN, side CM must be equal to side BN. Okay, so here side CM equals to side BN, but here before that we will implement here rule 19. According to rule 19, the perpendicular from the center of a circle towards any chord bisect the chord. In the drawing we have a circle, point O is the center of the circle, AB is the chord in this circle, so the perpendicular OM bisect chord AB. Again, the perpendicular OM from the center of this circle, that is to say from point O, bisect chord AB. That is to say, AM equals to MB. We can implement rule 19 in our drawing. Because in our drawing, from the center of this circle, that is to say from point O, we have perpendicular to chord BA. And therefore, according to rule 19, the perpendicular ON bisects chord BA. BA in total equals to 13. Therefore, each half must be equal to 6.5. The first half BN equals to 6.5 units in its length. And the second half of chord BA is also NA is also equal to 6.5 units in its length. We continue with rectangle BC, MN. Rectangle BC and M, side BN must be equal to the opposite side CM. But BN equals to 6.5, therefore the opposite side CM must be also equal to 6.5 units in its length. In the next step, we will do another construction. That is to say, from point A, we will go perpendicular on CD. Again, from point A, we will go perpendicular on CD. So okay, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and CD. This point is point L. In the next step, we will focus on the lower quadrilateral NMLA. In the lower quadrilateral NMLA, we have here perpendicular ON. So if we focus on the lower side of the perpendicular ON at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the lower side of the straight line NO at point M, we have this angle that is right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in quadrilateral NMLA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral NMLA, we have 4 right angles, and according to rule 5, quadrilateral NMLA is a rectangle. So that you know, the lower quadrilateral NMLA is a rectangle according to rule 5 because it has 4 right angles. So in the lower quadrilateral NMLA, side NA must be equal to the opposite side ML. But NA equals to 6.5, therefore the opposite side ML must be also equal to 6.5 units in its length. What is the length of this short line segment LD? From the drawing, it is very easy to see that LD in total equals to CD minus CL. Again, CD minus CL equals to LD. So it is now LD equals to CD minus CL. So LD in total equals to CD. CD equals to 18 units in its length, according to what is given in the question. Minus CL. CL in total equals to 6.5 plus 6.5, that is 13. So CL equals to 13. So in total we found out that LD equals to 18 minus 14, that is 5. LD equals to 5 units in its length. This is the short line segment LD. This is equals to 5 units in its length. In the next step, we will extend line segment DC by straight line until it touches the circle. And we will define the touching point of the extended line segment DC with this circle. This point is point T. By doing this construction, we create a deal called TD. This is called TD. And we have perpendicular OM from the center of the circle towards called TD. According to rule 19, the perpendicular OM from the center of the circle, that is to say from point O, the perpendicular OM by set called TD. Again, according to rule 19, the perpendicular OM by set called TD. That is to say, according to rule 19, TM equals to MD. Again, according to rule 19, the perpendicular OM by set called TD. That is to say, TM equals to MD. So write it down. TM equals to MD according to rule 19. So TM equals to MD. MD in total equals to 6.5 plus 5. Again, MD in total equals to 6.5 plus 5. 6.5 plus 5 is 11.5. MD equals to 11.5. And from this equation, TM equals to MD equals to 11.5. We have that TM also equals to 11.5 units in its length. TM equals to 11.5. From one side, TM equals to 11.5. But from the other side, TM equals to TC plus CM. Again, from the other side, TM in total equals to TC plus CM. So TM from one side it is equals to 11.5, but from the other side, TM equals to TC plus CM. And from this equation, we derive that 11.5 equals to TC plus CM. So 11.5 equals to TC. TC is the missing side, so we leave it as it is. Plus CM. CM equals to 6.5. So if we found out that 11.5 equals to TC plus 6.5. Here we will subtract 6.5 from this equation, and we get that the missing line segment TC is equal to 11.5 minus 6.5 is 5. So if we found out that this is the missing short line segment TC, that equals to 5 units in its length. TC equals to 5 units in its length. In the next step, we'll extend line segment BC by a straight line until it touches the circle. And we will define the touching point of the extended line segment BC with this circle. This point is point Q. By doing this construction, we created code BQ. Code BQ intersects with code TD at point C. Again, code BQ intersects with code TD at point C. So all the requirements of rule 15 are satisfied, and therefore we can implement rule 15. Repeat quickly on rule 15. According to rule 15, if code AB intersects with code CD at point O, then the following equation is true. AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So in the moment we have a circle, this is called AB that intersects with code CD at point O. So in this moment the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So can I implement rule 15 in our domain? Why put in our domain? We have code BQ intersects with code TD at point C. Again, code BQ intersects with code TD at point C. So all the requirements of rule 15 are satisfied, and therefore we can implement rule 15. So it is now, in our original domain, code BQ intersects with code TD at point C. The intersection point between code BQ and code TD occurs at this point C. So all the requirements of rule 15 are satisfied, and therefore we can implement rule 15. According to rule 15, TC times CD equals to BC times CQ. Again, TC times CD equals to BC times CQ. TC times CD equals to BC times CQ. And again, according to rule 15, the following equation is true, that TC times CD equals to BC times CQ. TC equals to 5 units in its length, times CD equals to 18 units in its length, according to what is given in the question, and it is equals to BC equals to 6 units in its length, according to what is given in the question, times CQ is the missing side, so we notice it is. So in total, we have found out that 5 times 18 equals to 6 times CQ. Here we will divide this equation by 6, and we get that 18 over 6 is 3, and 3 times 5 is 15. So in total we found out that CQ equals to 15 units in its length. This is 9 segment CQ, that equals to 15 units in its length. In the next step, we'll join points Q and A together by straight line. Again, we'll join points Q and A together by straight line. By joining points Q and A, we can do triangle QBA. This is triangle QBA. Triangle QBA equals to 90 degrees in size, according to what is given in the question. And triangle QBA subtend on chord QA. Again, triangle QBA subtend on chord QA. So we can implement rule 5. I'll repeat quickly on rule 5. According to rule 5, any triangle is equal to 90 degrees in size must subtend on the diameter of the circle. In the domain of a circle, this is triangle MAN, that is equal to 90 degrees in size. And therefore, according to this rule 5, triangle MAN must subtend on the diameter of the circle. And indeed, triangle MAN subtend on MN, that is the diameter of the circle. So according to this rule 5, any triangle that is equal to 90 degrees in size must subtend on the diameter of the circle. So we can implement rule 5 in our drawing. In our drawing, this is triangle ABQ that is equal to 90 degrees in size, and therefore, according to rule 5, triangle ABQ must subtend on the diameter of the circle. Triangle ABQ subtend on chord AQ, and therefore, according to rule 5, chord AQ must be the diameter of the circle. So I did not, if you found out that according to rule 5, chord AQ is the diameter of the circle. The diameter of any circle is twice as long as the radius. So if we define the radius of this circle as r, then the diameter AQ must be equal to 2r. AQ equals to 2r. So actually, this is the diameter AQ of this circle, that is equal to 2r. In the next step, I'll copy the right triangle ABQ in a new page, and we will implement the Pythagoras theorem on this right triangle ABQ. Here by PT is the progression from Pythagoras theorem. Side BQ of the right triangle ABQ equals in total to 15 plus 6, that is 21. According to what is given as the question, side AB equals to 16 units in incident. Side AB equals to 13 units in incident. Here, AB equals to 13. And the hypotenuse AQ is the diameter of the circle, therefore it is equal to 2r. So actually, this is the right triangle ABQ, that goes from the original domain. This right triangle ABQ, according to the Pythagoras theorem, QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. So write it down. QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. QA is 2r. Therefore QA squared is 2r squared. 2r squared is 4r squared. And it is equals to QB squared. QB equals to 21, therefore QB squared is 21 squared. That is 441 plus BA squared. BA is 13, therefore BA squared is 13 squared, that is 169. So in total we found out that 4r squared equals to 441 plus 169. 441 plus 169 is equal to 610. In conclusion, we found out that 4r squared equals to 610. Here we divide this equation by 4. And finally we get that r squared equals to 600 over 10 is 150. Again, 600 over 10 600 over 4, of course. 600 over 4 is equal to 152.5. 150. So r squared equals to 152.5. Our task is to find out the area of this circle. We know that the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of this circle must be equal to pi times the radius of the circle squared. The radius of the circle squared is r squared. So it is pi times r squared, and r squared is 152.5. So if we found out that the area that we are looking for this question, that is the area of this circle, is equal to either 152.5 pi square units in its size, or in terms of numbers it is equal to 479.09 square units in its size. So finish with the first method. Repeat again. Found out that the area of this circle is equal to either 152.5 pi square units in size, or in terms of numbers, the area of this circle is equal to 479.09 square units in size. So we finish with the first method. In the next step, I'll present to you how to find out the area of this circle according to the second method. In the second method, we'll use the things that we already found out in the first method. We have already found out in the first method that line segment CQ equals to 15 units in length. Again, line segment CQ equals to 15 units in its length. This is line segment TC, this is equals to 5 units in its length. So here we can implement rule 26. I'll repeat quickly on rule 26. Rule 26 is true in any circle. So in any circle, if two chords intersect with each other at a straight line, if two chords intersect with each other at a right angle. So here we have a circle, and chord AB intersects with chord CD at a right angle at 90 degrees. Again, chord AB intersects with chord CD at a right angle at 90 degrees. So in this drawing, the following equation will be true. That a all square plus ob square plus c all square plus od square equals to 4r square. And r is the radius of the circle. And again, in this drawing, chord AB intersects with chord CD at 90 degrees. So in this drawing, the following equation is true. That a all square plus ob square plus c all square plus od square equals to 4r square. Okay? So we can implement rule 26 in our drawing. Why? Because in our drawing, we have chord TD intersects with chord BQ at 90 degrees. Again, chord TD intersects with chord BQ at 90 degrees. So all the requirements of rule 26 are satisfied, and therefore we can implement here rule 26. So I write it down. If you found out that in our drawing, chord TD intersects with chord BQ at 90 degrees. This again is right angle. And the intersection point occurs at this point C. Repeat again. In our original drawing, we have chord TD that intersects with chord BQ at 90 degrees. It intersects with each other at 90 degrees. Chord BQ intersects with chord TD at 90 degrees, and the intersection point is here, occurs at point C. So all the requirements of rule 26 are satisfied, and therefore we can implement here rule 26. According to rule 26, the following equation will be true. That TC square plus CD square plus BC square plus CQ square equals to 4r square. And again, according to rule 26, the following equation will be true. The TC square plus CD square plus BC square plus CQ square equals to 4r square. R is the radius of this circle. That is, we are looking for the radius. After we find out the radius, the area of the circle will be equal to pi times the radius squared. TC is 5, therefore TC square is 5 squared, that is 25, plus CD square. CD is 18, therefore CD square is 18 squared, that is 324, plus BC square. BC is 6, therefore BC square is 6 squared, that is 36, plus CQ square. CQ is 15, therefore CQ square is 15 squared, that is 225, and it is equal to 4r square. So if you found out that according to rule 26, 25 plus 324 plus 36 plus 225 equals to 4r square. 25 plus 225 is 250 plus 324 plus 36 equals to 360, is equals to 4r squared. So if you found out that 250 plus 360 equals to 4r squared. 250 plus 360 is 610 equals to 4r squared. Or 4r squared equals to 610. Here we divide this equation by 4 and we get that r squared equals to 610 over 4 is 152.5. So r squared equals to 152.5. Our task is to find out the area of this circle. The area of any circle equals to pi times the radius of the circle squared. And therefore, the area of this circle must be equal to pi times the radius of this circle squared. The radius of this circle squared is r squared. So it is pi r squared. So it is pi times r squared, and r squared is 152.5. So in total, we found out that the area of this circle is equal to either 152.5 pi square units in size, and in terms of numbers, it is equal to 479.09 square units in its size. So actually, in both methods, we arrive to the same result, that the area of this circle equals to either 152.5 pi square units in its size, and in terms of numbers, the area of this circle equals to 479.09 square units in its size. So we finished with the second question. In the next step of some of the lecture, we start with the first question, of course. In the first question, our task is to find out the radius of this circle. So, in the moment we have a circle and a right triangle, triangle ABC. This is angle ABC, this is the right angle. This is side AB of the right angle ABC, that equals to 13 units in its length. This is line segment AD. Again, this is side AB of the right triangle ABC, that equals to 4 units in its length. This is line segment AD, that is also equals to 4 units in its length. This is line segment DC, that equals to 1 unit in its length. Again, our task is to find out the radius of this circle. So here we implemented rule 25. According to rule 25, if from a common external point we draw a tangent to a circle and a line segment that cuts the circle at 2 points, then the following equation is true, that PA squared equals to PB times PC. So we can implement rule 25 in our drawing. Why? Because in our drawing we have, if we focus on this common standpoint point C, from this common standpoint point C, we have tangent CE that is tangent to this circle at point E, and we have line segment CA. This is also defined as a secant, and line segment CA plus the circle at 2 points, D and A. So all the requirements of rule 25 are satisfied, and therefore we can implement the rule 25. According to rule 25, open again. According to rule 25, the following equation is true, that CE squared equals to CD times CA. Again, CE square equals to CD times CA. CE square equals to CD times CA according to Rule 25. CE is the missing sign, so we leave it as it is. So it is CE square equals to CD. CD is 1 times CA. CA in total equals to 3 plus 1, that is 4. Again, CD is 1 and CA is 4. So in total, CE square equals to 1 times 4, that is 4. So CE square equals to 4. Here to go out of the equation, if I found out that CE, tangent CE equals to 2 units in its length. This is tangent CE, that equals to 2 units in its length. In the next step, I copy the right triangle ABC in a new page and we implemented the Pythagoras theorem in this right triangle ABC. According to the Pythagoras theorem, in any right triangle, the sum of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is right triangle ABC, that is coming from the original domain. This right triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC squared equals to AB squared plus BC squared. AC is 4, therefore AC squared is 4 squared, that is 16, and it is equals to AB squared. AB is 3, therefore AB squared is 3 squared, that is 9, plus BC squared. BC is the missing sign, so we need to see it is. So in total, if you found out that 16 equals to 9 plus BC squared. Here we subtract 9 from the equation, and find out that 16 minus 9 equals to 7, so BC squared equals to 7. Here we took out of the equation, and find out that the missing sign BC is equal to 7, to the square root of 7 units in its length. This is side BC of that triangle BC, and it is equal to the square root of 7 units in its length. So what is the length of this missing line 7BE? BE equals to BC minus EC. And again, B equals to BC minus CC. So B equals to BC, that is square root of 7, minus CE, that is 2. So in total, B equals to the square root of 7 minus 2 units in its length. In the next step, from point O, that is the center of this circle, we do perpendicular on BC. We join points O and E together by straight line. Point O is the center of the circle, point E is the point of the circle itself, therefore OE is the radius of this circle. We define the radius of this circle as R, so O equals to R. The radius OE is equals to R, the radius OE is drawn to point E, that is the point of tendency of the BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to Rule 1. In the next step, we did the construction, that is to say, from point O, that is the center of this circle, we do perpendicular on AB. Again, from point O, we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. So by doing this construction, we can do the quadrilateral FOEB. In quadrilateral FOEB, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this fourth again. In total, they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth again must be equal to 90 degrees in size. So inside quadrilateral OFBE, we have 4 rectangles. And therefore, according to Rule 5, quadrilateral FBEO is a rectangle. Quadrilateral FOBE is a rectangle according to Rule 5 because it has 4 rectangles. Before we continue, what is the length of this? So we continue with the rectangle. In rectangle FOEB, the opposite sides must be equal to each other. That is to say, side OE must be equal to the opposite side FB, but OE is R, therefore the opposite side FB must be also equal to R. Likewise, according to the symbol, the same rectangle FOEB, side BE must be equal to the opposite side FO. but BE is square root of 7 minus 2, therefore the opposite side F4 must be also equal to the square root of 7 minus 2 units in its length. What is the length of this missing line segment AF? AF equals to AB minus FB. Again, FA equals to AB minus FB. So AF equals to AB, AB is 3, according to what is given in the question, minus FB, FB equals to R. So in total, AF equals to 3 minus R. AF equals to 3 minus R. In the next step, we join points A and O together by straight line. Point O is the center of the circle, point A is the point of the circle itself, therefore OA is the radius of this circle, that is equals to R according to our definition. In the next step, I copied the right triangle AF4 in the new page and we implemented the Pythagoras theorem on this right triangle AF4. This is the right triangle AF4 that is according to the original domain. In this right triangle AF4, AO squared, that is the square of the hypotenuse, equals to AF squared plus FO squared. AO squared equals to AF squared plus FO squared. AO is R, therefore AO squared is R squared, and it is equals to AF squared. AF is 3 minus R, therefore AF squared is 3 minus R squared, plus FO squared. FO is square root of 7 minus 2, therefore FO squared equals to square root of 7 minus 2 squared. So in total, we should find out that R squared equals to 3 minus R squared, plus square root of 7 minus 2 squared. So R squared equals to 3 minus R squared. Here we open the brackets and we found out that 3 minus R squared equals to 3 squared, that is 9, plus R squared, minus 2 times 3 times R, that is minus 6R, plus square root of 7 minus 2 squared. Square root of 7 minus 2 squared in total equals to 0.417. So in total we should find out that R squared equals to 9 plus R squared, plus 6 plus 0.417. We have R squared on both sides of this equation, so R squared will get cancelled. After we cancel R squared on this side of the equation, we left with nothing, that is to say 0. While on the other side of this equation, we have 9 plus 0.47 is 9.417 on 6 R. So in total, we should find out that 0 equals to 9.417 on 6 R. Here we added 6R to this equation. If I found out that 6R equals to 9.417, here we divided the equation by 6 and finally found out that R, that is the radius of this circle, R equals to 1.57 units in its length. So if we found out that the radius of this circle, that is the radius that we are looking for this question, is equal to 1.57 units in its length. So we finish with the first question. In the next step, I presented to you the second question, and we solved the second question in two different methods. In the second question, our task is to find out the area of this circle. So in the following we have a circle. This is line 7BC, that equals to 6 units in its length. This is line 7BA, this equals to 13 units in its length. Or chord BA equals to 13 units in its length. This is line 7CD, that equals to 18 units in its length. Again, our task is to find out the area of this circle. So first of all, we define the center of this circle. This point is point O, and from point O, we go perpendicular on CD. But before that, we have here all 27. According to all 27, we have those two one-sided triangles. The sum of those two angles is 180 degrees, and therefore according to all 27, they are located between two parallel lines. That is to say, BA is parallel to TC to CD according to all 27. I mean, again, BA is parallel to CD according to all 27. BA is parallel to CD. We find the center of this circle. This point is point O. From point O, we go perpendicular on CD. Again, from point O, we go perpendicular on CD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and CD. This point is point M. Then we extend line segment to OM, or the perpendicular OM, by straight line until it touches the side BA, called BA. We define the touching point of the extended perpendicular OM with code BA. This point is point N. And because of the fact that code BA is parallel to code CD according to 27, it means that the perpendicular to CD will be also perpendicular to BA. So the extended perpendicular OM must be also perpendicular to code BA. So this angle equals to 90 degrees and this angle equals to 90 degrees because they are parallel to each other. So we have here quadrilateral BCMN in quadrilateral BCMN, but before that we can implement here Rule 19. The perpendicular OM, the perpendicular ON towards chord BA bisects chord BA. Again, according to Rule 19, the perpendicular ON towards chord BA bisects chord BA. BA total is 13, therefore each half must be equal to 6.5. That is to say, the first half VN is 6.5 and the second half NA is also 6.5, according to Rule 19. So in the upper quadrilateral BCMN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces again, in total must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 pieces again must be equal to 90 degrees in size. So in size quadrilateral BC and M we have 4 right angles. And therefore, according to Rule 5, quadrilateral BC and M is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle BCMN, side BN must be equal to the opposite side CM. But BN is 6.5, therefore the opposite side CM must be also equal to 6.5 units in its length. In the next step, we join points A. From point A, we draw perpendicular on CD. Again, from point A, we draw perpendicular on CD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. We define the touching point of the perpendicular from point A and call CD. This point is point L. So ON is a perpendicular. As a perpendicular, it is absolutely a straight line. So if we focus on the lower side of the straight line ON as point M, here the sum of the angles must be equal to 180 degrees according to Rule 3. So which angles we have at the lower side of ON at point M? We have this angle that is right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to Rule 3. Therefore, this missing angle must be equal to 90 degrees in size. So in size quadrilateral MNAL, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of these 4 pieces again, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore these 4 pieces again must be equal to 90 degrees in its size. So inside quadrilateral MNLA we have 4 right angles, and therefore according to Rule 5, quadrilateral MNMAL is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NMLA, side NA must be equal to the opposite side ML. But NA is 6.5, therefore the opposite side ML must be also equal to 6.5 units in its length. What is the length of this short line segment LD? LD equals to CD minus CL. Again, LD equals to CD minus CL. So LD equals to CD, that is 18, minus CL, that is 6.5 plus 6.5, 13. That's 13. So in total, LD equals to 18 minus 13, that is 5. So this short line segment LD equals to 5 units in its length. In the next step, we extended line 7 DC by straight line until it touches the circle, and we define the touching point of the extended line 7 DC with this circle. This point is point T. By doing this construction, we created here chord TD. This is chord TD, and we have perpendicular OM towards chord TD, perpendicular OM towards chord TD, bisect chord TD. Again, according to rule 19, the perpendicular OM that is from the center of this circle, that is also from point O, towards chord TD, bisect chord TD. If perpendicular OM bisect chord TD, it means that TM equals to MD. TM equals to MD according to rule 19. TM equals to MD according to rule 19. TM equals to MD, but MD in total equals to 6.5 plus 5. 6.5 plus 5 is 11.5. So MD equals to 11.5, and from this equation TM equals to MD equals to 11.5, we derive that TM also equals to 11.5. So this line 7 TM is equal to 11.5. But TM from one side is equal to 11.5, but from the other side is also equals to TC plus TM. So you can write here that from one side TM equals to 11.5, and from the other side is equals to TC plus CM. So TM equals to TC, TC is the missing size of relative CTs, plus CM. CM equals to 6.5 units in its length. So in total we found out that 11.5 equals to TC plus CM, and CM equals to 6.5, therefore 11.5 equals to TC plus 6.5. Here we subtract the 6.5 from this equation, and finally found out that the missing side TC equals to 11.5 plus 6.5 is 5. This is the missing side TC. This is equals to 5 units in its length. In the next step, we extended line 7 BC by straight line until it touches the circle. We define the touching point of the extended line 7 BC with this circle. This point is point Q. By doing this construction, we can do the chord BQ. This is chord BQ that intersects with chord TD at point C. Again, chord BQ intersects with chord TD at point C. Therefore, we can implement here all 15. According to all 15, chord AB intersects with chord CD at point O. Chord AB intersects with chord CD at point O. So in this moment, the following equation is true, that AO times OB equals to CO times OD. AO times OB equals to CO times OD. So we can implement all 15 in our drawing. Now in our drawing, chord TD intersects with chord BQ at point C. Okay. Chord BQ intersects with chord TD at point C. So all the requirements of all 15 are satisfied, and therefore we can implement all 15. According to all 15, the following equation is true, that TC times CD equals to BC times CQ. Again, TC times CD equals to BC times CQ. TC times CD equals to BC times CQ. TC is 5, CD is 18, BC is 6, and CQ is the missing side. So in total, we found out that 5 times 18 equals to 6 times CQ. Here we divided the equation by 6 and found out that CQ equals to 18 over 6 is 3, so, and 3 times 5 is 15. So in total CQ equals to 15 units in its length. This is the missing side CQ, that is equals to 15 units in its length. In the next step, we join points Q and A together by straight line. By doing this construction, we can do peripheral angle ABQ. Verify again ABQ equals to 90 degrees in size. And according to rule 5, any triangle that is equal to 90 degrees in size must subtend on the diameter of the circle. Triangle angle ABQ is equal to 90 degrees in size, and therefore it must subtend on the diameter of the circle. Triangle ABQ subtend on AQ, and therefore according to rule 5, AQ must be the diameter of the circle. In the next step, we implemented the Pythagorean theorem on this right triangle ABQ. This is the right triangle ABQ that is according to the original drawing. According to the Pythagorean theorem, QA squared equals to BQ squared plus BA squared. QA is 2R, therefore QA squared is 2R squared, that is 4R squared, and it is equals to BQ squared. BQ is 21, therefore BQ squared is 21 squared, that is 441, plus BA squared. BA is 13, therefore BA squared is 13 squared, that is 169. So in total, if you found that 4R squared equals to 441 plus 169. 441 plus 169 is 610. So in total, if you found out that 4R squared equals to 610, here we divided the equation by 4 and found out that R squared equals to 152.5. Our test is to find out the area of this circle. We know that the area of any circle equals to pi times the radius of the circle squared, and therefore the area of this circle must be equal to pi times the radius of this circle squared. The radius of this circle is r, therefore the radius squared is r squared. So the area of this circle must be equal to pi r squared, and r squared is 152.5. So we substitute r squared by 152.5, and in total we found out that the area of this circle that is that we are looking for in this equation, it is equal to either 152.5 pi square unit in size. In terms of numbers, the area of this circle is equal to 179.09 square unit in size. So we finish with the first method. In the next step, I present to do the second method and solve the question according to the second method. In the second method, we used with the figures that we already found out in the first method. We already found out that line segment CQ equals to 15 units in incident, and line segment TC equals to 5 units in incident. So here we can implement rule 26. According to rule 26, rule 26 is true in any circle. In any circle, if two chords intersect with each other at a right angle, then the following equation is true. Here, chord AB intersects with chord CD at point O at 90 degrees. Because with each other 90 degrees. So this the following equation is true, that AO squared plus OB squared plus CO squared plus OD squared equals to 4R squared. And R is the radius of this circle. So we can implement rule 26 in our drawing, because in our drawing we have chord TD that intersects with chord BQ at 90 degrees at point C. So all the requirements for rule 26 are satisfied, and therefore we can implement here rule 26. Again, in our drawing, chord TD intersects with chord BQ at 90 degrees at point C. Therefore, the following equation will be true, that TC squared plus CD squared equals to TC squared plus CD squared plus BC squared plus CQ squared equals to 4R squared. Again, according to rule 26, the following equation is true, that TC squared plus CD squared plus BC squared plus CQ squared equals to 4R squared. TC is 5, therefore TC squared is 5 squared, that is 25, plus CD squared. CD is 18, therefore CD squared is 18 squared, that is 324, plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 36, plus CQ squared. CQ is 15, therefore CQ squared is 15 squared, that is 225, equals to 4R squared. 25 plus 225 is 250, and 324 plus 36 is 360. So in total, if you found out that 250 plus 360 equals to 4R squared. 250 plus 360 is 610, so 610 equals to 4R squared. Here we divided the equation by 4 and found out that R squared equals to 152.5. Our test is to find out the area of this circle. I'm sure you know that the area of any circle equals to pi times the radius of the circle squared. And therefore the area of this circle must be equal to pi times the radius of this circle squared. The radius of this circle squared is pi r squared, and r squared is 152.5. So we solve it as square by 152.5 and find formula that the area of this circle, according to the second method, equals to pi times 152.5 square units in size. So in terms of numbers, the area of this circle equals to 479.09 square units in size. So in both methods, we arrive to the same result. The area of this circle equals to either 152.5 square units in size. So in terms of numbers, it is equal to 479.09 square units in size. Okay, thank you very much.